In this talk, I would like to give you an idea of the scope and of the character of this research. Obviously, I will not even try to present a complete survey. Instead, I will focus on a few research efforts, picking ones closer to my heart, closer to this lab, also closer to the present and perhaps to the future. For our present purposes, we could say that the present starts with a famous memo by Bill Gates. In this memo from early 2002, very soon after this lab was founded, Bill Gates set trustworthy computing as the top priority for the company. Although trustworthy computing has several important aspects, security certainly received a huge amount of the attention. Around the time of Bill Gates' memo, one school of thought on security said that, by and large, we know plenty of mechanisms that could improve security if they were applied, but that what was lacking was the will to deploy these mechanisms. There is perhaps some truth to this point of view. However, it ignores the fact that computers and computing systems are always changing, and that attacks are changing too. The defenses must evolve as well. In addition, as the stakes get larger, we may want higher confidence, higher assurance about the defenses, old or new. And we may also be prepared to make different trade-offs between security, compatibility, and performance. With this in mind, one way of organizing our thinking about the defenses is in terms of Butler Lamson's golden rule, or gold standard. Butler, who is now in the New England lab, wrote that there are three basic mechanisms for implementing security, and that together they form the gold standard for security. Authenticating principles consist in answering the question, who's said that or who's getting that information. Authorizing access consists in answering the question, who can do which operations on this object. And finally, we also need auditing, which concerns examining the decisions of the guard in order to figure out what happened and why. These three mechanisms should be understood as pieces of the implementation of security policies within models of security. Today, however, I will not get into details on security models and security policies, but I will tell you about some research work on each of these three mechanisms, starting with authentication. One important way of performing authentication is with cryptographic protocols. In this approach, users, computers, and other principals can be associated with secret cryptographic keys, which are used for identifying them. So the story goes, we may, for example, have two users, Alice and Bob here, who know the same key K, and then Alice may use this key for signing or for encrypting a message that she may send to Bob on a public channel, such as the internet, despite the presence of Eve here and other attackers. A signature can ensure the authenticity of the message that Bob receives, and encryption, its secrecy. In general, cryptographic protocols are not so simple, of course. There is a long, illustrious history of cryptographic protocols, full of clever ideas, but also full of subtleties and of vulnerabilities. Because of these vulnerabilities and subtleties, there has been a lot of interest in developing rigorous methods for the design and analysis of cryptographic protocols. For example, the protocols may be expressed in a programming language called the process calculus, then verified using theorem provers and other such tools. In a process calculus, Alice might simply be defined as a program that sends a message M protected under the key K on the channel internet. Similarly, Bob might, for example, be defined as a program that receives a message X on internet, then checks that the message is protected under K, and then proceeds. And their combination is a system in which they run in parallel. This vertical bar here is the parallel composition operator, using a fresh private key K. Within Microsoft, we have developed this idea and applied it to a number of protocols, some part of product efforts, some coming from elsewhere. It is only quite recently that this line of research has reached the maturity of allowing us to reason about some actual implementations of important protocols written in languages such as C or F#. The epicenter of this progress in the last few years has been somewhere between the Cambridge lab and the MSR INRIA Joint Center in France. For instance, they have written a reference implementation of TLS, which is the IETF standard for SSL, in F#, then compiled it to a process calculus, and then analyzed it automatically using a sort of theorem proving tool. Of course, not all authentication relies on cryptography. Sometimes, for instance, we employ usernames and passwords for identifying users and the like. Sometimes even weaker indicators can help for tracking users and computers. These may include, for example, IP addresses, and also browser cookies and other identifiers for browsers. The tracking may obviously raise privacy concerns, and it is not perfect, but it can be quite helpful, particularly when combined with other techniques. We rely on some of these identifiers in some of our work on auditing, to which I will return in a few minutes. No matter how authentication is done, its result is often the input to an authorization decision. Authorization happens at many levels in systems. Here we'll tell you about a family of projects focused on low-level attacks and low-level defenses. Basically, we consider situations in which various pieces of code, not all equally trusted, share an address space. Such situations arise commonly in operating systems, browsers, and in other settings. And then we are interested in questions such as, is it okay to write to this address in memory, or is control allowed to jump to this instruction? This latter kind of question about the flow of control is essential for authorization. Fundamentally, we must enforce that the flow of control conforms to the expected control flow graph, or in other words, that we have control flow integrity. If we cannot restrict the control flow of programs, then we cannot guarantee that they do not circumvent the checks on which security depends. In fact, many attacks over the years rely on buffer overflows and other low-level vulnerabilities precisely in order to subvert control flow. Languages such as Java and C# can help in those situations. These high-level languages and their type systems can help enforce fundamental properties of control flow and of memory accesses, properties that are not generally true for arbitrary binaries. For example, with these languages, we can often guarantee that when a function f1 calls another function f2 and control is transferred from f1 to f2, the control flow goes to the beginning of f2's body and not to the middle. If the beginning of the body contains a check that aims to guarantee that it's safe to perform a certain operation, and the middle contains the operation itself, then this guarantee implies that the check cannot be circumvented. This use of languages for security was a very frequent theme in work a few years ago, and it remains quite important. However, there is still a huge amount of code that is not written in those languages. Moreover, despite a lot of progress in fixing buffer overflows and other low-level vulnerabilities, and also a lot of progress on tools like the tool Sage from Redmond for finding vulnerabilities, we have to be mindful of the possibility that we may not be able to find and to eliminate all buffer overflows or all other mistakes in code. We can look at this as a setback, but we can also look at this as a sort of opportunity. In fact, there are several research efforts that start from the somewhat depressing premise that vulnerabilities exist in software and that they may always exist, and then look for good next moves. In this direction, one idea which we explored in this lab in collaboration with colleagues in Redmond is to add instrumentation to binaries by rewriting the binaries. An attractive variant which has been explored in the MSR lab in Cambridge is to rely on compilers for inserting the instrumentation. In either case, the instrumentation will appear just before control flow transfers, and at runtime it will check that the targets of these transfers are allowed by a given policy. Again, several options are open for how this is done. One possibility is to place a distinct label at the allowed targets of control flow transfers, and then to check for the presence of the label just before each transfer. For example, we could insert the label 1, 2, 3, 4, 5, 6, 7, 8 at the start of the check, and the different label 2, 4, 6, 8, 3, 5, 7, 9 just before the operation. And at every place where there is a computed jump, say a call instruction, we could insert a verification that ensures that the target address of the jump contains the expected label, for example, 1, 2, 3, 4, 5, 6, 7, 8, so that in particular, the jump does not go directly to the operation if it should instead go to the check. Another possibility, as an alternative to this use of labels inserted into the code, is to set up and to manage an auxiliary data structure that encodes the allowed transfers of control. Whichever of these possibilities is adopted in implementation, one very attractive property is that we can actually prove formally, rigorously, that control flow has the expected properties, that it follows the expected control flow graph. This is in contrast with a lot of work on useful but imperfect mitigations like stack guard and some practical forms of layout randomization, which attackers typically find hard to circumvent or break, but which sometimes don't cut it. So we're working on authentication and authorization, but authentication and authorization don't always do very much or don't work as expected. So we also need auditing. This is particularly true for many services where authentication and authorization are quite modest or quite rudimentary. An example of this is a free email service. In such a service, it is generally very easy for anyone or almost anyone to set up an account and to begin to send and to receive email. It is also fairly common for user passwords to be stolen or to be guessed by attackers. So one challenge then is to distinguish legitimate users from spammers and from other attackers. Another challenge is to detect when accounts have been compromised and to disable those accounts or to try to recover them. This can be seen as two auditing tasks. For instance, in one very recent project, an ongoing project, we use social graphs for distinguishing likely good accounts from bad accounts in Hotmail. Suppose that we make a graph where the nodes represent users of the email service, and we place an edge between two nodes if the corresponding accounts communicate sufficiently in both directions for a suitable value of sufficiently. So, for example, there may be an edge between Alice and Bob because they send lots and lots of email to each other, but there would not be an edge between the attacker and Bob because although the attacker might send a lot of spam to Bob, Bob might not reply very often. It turns out that in this social graph, there's a huge connected component in which most accounts are good. So we may use membership in this huge connected component as a very useful signal in distinguishing good accounts from bad accounts. Of course, there are many variants on these ideas. Overall, it looks like a very intriguing and a very promising approach. Another facet of our work on auditing concerns web search. Much like in the case of free email services, anyone or almost anyone can do web searches. and almost anyone can set up web pages that may get indexed, and those web pages may, of course, contain deceptive contents or malware. So in collaboration with Binks and with colleagues from academia, we have been exploring the ways in which attackers try to abuse search engines. One facet of this work is a system called search audit. We look at the Bing query stream. We know a priori about a few malicious queries and about some malicious source IP addresses. Then we generalize, and we try to find more queries and more source IP addresses. For instance, we can construct regular expressions that contain all the known malicious queries, and then we see what we discover. In particular, it turns out that one very large group of malicious queries is looking for strings that would identify vulnerable web servers. For instance, suppose that an attacker knows that the software package called Data Life Engine contains some vulnerabilities. It may search for the string powered by Data Life Engine and then try to compromise the servers with web pages that contain the string. We found that attackers employ searches in this and several other ingenious ways. Search engines are a powerful tool and not only for legitimate good users. But examining the anonymized search logs, we can often understand the attacks and their trends, and we can often block them. Another facet of our work on auditing for web search is a system called SEO, or DSEO, where SEO stands for Search Engine Optimization, of course. This system helps us look for web pages put up by attackers on compromised servers. For instance, an attacker may create a page that gets included in the results for some popular searches, and when a user goes to the page, it generates a pop-up that pretends to be an antivirus program and tries to scare the user into doing something foolish and dangerous. It turns out, however, that those bad web pages have some properties and some regularities that can help us identify them. For instance, their URLs are generated automatically by attackers, so they often have common structures and patterns that we can use for recognizing them. In these projects on auditing, and in many other projects in MSR, one salient characteristic is that we rely on huge amounts of data, such as the anonymized logs of Hotmail and Bing, and on large-scale infrastructures for data analysis, like DryadLink that Mihai Budiu mentioned earlier today. In addition, we have fairly rich interactions with product groups. Not all interactions are alike, but generally the interactions are rather easy and productive. A third characteristic of the research is that we're generally playing defense. Like researchers in academia and in many security companies, we spend some of our time looking for vulnerabilities for attacks against Microsoft products and against other systems. But generally, that is not the main focus of our work. As we're speaking of defense, I will leave you with this drawing of a guard as a final image. During the French Revolution, the designer Jean de Mostyn de Gourcq designed a set of playing cards, of which I have a reproduction here, in which the kings, the queens, and the jacks disappeared, were eliminated, and they were replaced with more revolutionary images to do with freedom, equality, and so on, liberté, égalité. And there were cards with images for other good things like courage, enlightenment, and what else? Enterprise, which I have here. And curiously, the set included also a card for security, the card that you see on the screen. I say curiously because one does not usually think of security as an exciting revolutionary concept, but certainly some degree of security is crucial for many of the revolutionary applications of computing. Thank you.